Yeah, we're here to give you guys an update on the third day of the Kīlauea volcano summit eruption 2020. Eruption continues, still going strong. There's a lot of lava coming out of the vent. You can see the northern fissure, the most productive one right here in this first screen we have for you guys. So we're gonna take you guys through, as usual, the videos and photographs. We're gonna take you through some of the most pressing questions we've been getting asked. Questions like, what's going to happen if the lava level comes up and buries this vent that you guys see over here and kind of goes above it? Or when will the lava get high enough where I can see it from a public overlook? Or when will it spill over out of that inner crater? How long would that take? Or things like that. So we're going to make some guesses at that using some calculations. USGS is putting out more and more information and much more data, so we're going to go through all of everything they have and then kind of try to add a little bit more analysis for you guys as well. So we're going to start off with these videos up here. And here we have a video of the northern fissure. This is from yesterday. So you guys can see the bubbling fountain right there in the middle right there. I'll let that play for you guys. You can see that the lava level has come up to the bottom of that vent. Yeah, it actually used to be that the vent had a higher part and then a lower part, and then now the lower part's buried and the lake is kind of lapping up onto it and the higher part's pouring over. Now we're looking at the western fissure, and this is the less active, but at this kind of telephoto view, you can see it's actually still pumping. There's quite a lot of lava coming out of there. Not as much as the other one. Right. So yeah, that's interesting. I'll let it play for you guys again here. So I think there are some more things worth pointing out. So the first question that we've been getting is what happens when lava level actually comes up and gets below that. And I addressed that a little bit in last night's update, for those of you guys had a chance to watch that, because one thing we've talked about is Kīlauea Iki. And Kīlauea Iki was an eruption that had 17 different fountains in a 1 month eruption that it lasted, in the 36 days that it lasted. But the first phase was very different in the sense that it was like what we're seeing now, where we had a vent on the side of the crater, lava was pouring down into it, it was filling the whole thing up from the top down, and the whole other 17 phases of fountains had to do with the fact that the lava had drained the actual vent. So we'll visit that again in a little bit here, but one possibility is that we have to balance out the pressure of lava coming out of the ground with a weight that could hold it in from above. And of course, you got to remember that this is actually a blade of lava that's got fingers, right? This being one finger we're looking at in this video right here. And when we switch, we'll look at the western fissure, and this is now another blade, another finger of it. It's coming up to the side. And so they're both active at the same time. And, it could be that they're connected, not that far down. Right, so possibly, one thing that could happen is that we could actually see a shift in dynamics of one vent to the other. And it's interesting to watch this video that we're seeing right now and then compare it to the videos in the future and see what happens with that as the level of lava changes. So here we have another video. Oh, let me come back and stop this one. Okay, so this is now a helicopter overflight from yesterday, looking in and around the crater. Oh, excuse me. Chair just snapped back. Right, so here's the video. Yeah, so this is a famous USGS used helicopter pilot, David Okita with Volcano Helicopters, who is an expert flyer. We've been with him before. And you can see he's flying around the edge of the crater, right? They definitely doesn't want to put the aircraft in any dangerous situation, like going over that thing and maybe where the thermals and the updrafts might affect that. The gas might be hard to breathe. Yeah. I think usually it doesn't, rarely does it ever have doors on it. So, you know, it's really an extent of the gas and everything too, but it kind of really lets you know what's going on with all your senses as you're flying around. So you can kind of see he's coming up the edge of the crater wall over here. That's fascinating, right? Now here we are over the outer crater wall. There is an old road that remains. You got a glimpse of a flow. We're kind of looking to the southwest and kind of panning to the south. And now we're kind of going more southeast. There's some of that's Mauna Ulu cone. Here, I gotta get this brush going. Apologies. So I'll back it up a little bit just to show you guys here. All right, we're kind of looking down like over the path. Right over here is a 1974 lava flow. Some pit craters, Mauna Ulu, Kanuyohamo, Pu'o'o is over there. This is Kīlauea crater right over here. We're going to talk about this one later. This is the cinder pile that was left behind after the giant fountains of lava. We're panning around now. Mauna Kea, Mauna Loa is back here behind this cloud. We're looking back to the north now. You can see the innermost pit now has a flat bottom that's coming up. But something that's hard to see unless you're really on this western rim over here where USGS can make measurements. Or farther back over here, somewhere kind of closer beyond public access. Right. So I'm gonna start off kind of taking you guys just the cursory overlook at the webcams. This is from a couple hours ago, so we can kind of look at that these images and kind of reload it here. Give it another quick peruse. Views, you can see bright glow. Right, we have this kind of ash cloud coming up, and right over there, the wide angle shows a little bit better. Right, quite a lot of light coming from the crater walls down over here, and there's our most recent thermal image. We will look at that shortly as we do every update. And then this camera doesn't really show anything. It's kind of not pointing at anything glowing. But this is another camera worth looking at down here from the Mauna Loa Strip Road. Is one that was fairly recently added, KP cam. And this one is up at, I would guess, in the range of 6,600 feet. And it's looking down at Kīlauea from above. And so you can kind of see the big gas plume, right, being lit up by the glow of the fountains that are coming up from right down in here. Okay, so big picture kind of view. So let's reload it and see if it changes anything. So it's a little brighter. And still quite a lot of gas. This one's really quite right here at the top, yeah? Very interesting. We'll have to take a look at the thermal of that here shortly. So, but first let's look at what's happening with the USGS update. This is the USGS update page, and they're now switched because we're at alert level watch, color code orange for aviation. We're now getting daily updates. Oh. Okay, sorry guys, we're having some technical issues. Let me just take a second here and try to figure out what's going on. So sorry, you guys. I'm just trying to fix the audio. What's happening with Dane here? I'm not sure. I'm able to get him. Yeah, sorry, coming you guys a little bit later than we thought tonight. Also, it's been one of those nights with the technical issues here. So All right, so I seem to have lost Dane's audio tonight, and so he's making signs over there, and he's urging me to just get on with it already. So I will. And we were at alert level watch, color code all orange, so we're getting daily updates. We had an update today, just before 9 a.m. And what they're saying is no significant change. Kīlauea continues to erupt at its summit from 2 vents on the north and northwest sides of Halema'uma'u. As of late yesterday afternoon, the growing crater lake was 143 meters, 470 feet deep, with a surface area of 22 hectares, 54 acres, as the 2 emissions continue. So that number is now much outdated. The most recent number we have is 521 feet. I believe that is 156 meters. And a surface area, I don't have a current number for that. Summit tilt meters continue to record steady deflationary tilt. SO2 emission rates remained elevated, high, estimated around 30,000 tons per day as measured on Monday. Seismicity remained elevated but stable, with a few minor earthquakes and tremor fluctuations related to the vigor of fissure fountaining. Halema'uma'u lava lake observations. Of the 3 vents that erupted Sunday evening, December 20th, from the north and northwest walls of Halema'uma'u, 2 remain active this morning. The west vent, which is located on the lowest downdrop block within Halema'uma'u crater, is feeding 2 narrow channels into the lake. The north vent remains the most vigorous. The vents continue to feed lava into a rapidly enlarging lava lake filling Halema'uma'u crater. As of yesterday afternoon, the lake surface was 143 meters, 470 feet deep, with an approximate lake volume of 12 million cubic meters. So it's a little tedious to read through all this stuff, but this number ends up being very, very important, because if we actually can have a volume and a depth at the same time, we can then start making some calculations and projections of what's happening with this vent. And we'll get to that here shortly. So surface area 54 acres and roughly oval, about 700 yards by 400 yards, 450 by 750, 690 meters by 410 meters. There are some thermal maps. We'll get to the maps here a little bit later. An island of cooler solidified lava within a lava lake has been getting smaller and drifting eastward in the lake yesterday through this morning. It appears to be about 150 meters in diameter. So there is another piece of information we might not get unless we read through this update. So I know you probably guys can't actually read the text, but that's why I'm just highlighting for you guys where I'm getting this from. This is actually USGS information. All right, so let's move on from there and show you guys the photo and video chronology. So if you're on the main USGS page, it looks like this. There's all kinds of new hot links they've put in, so you guys can jump straight to the Kīlauea stuff. But you can also scroll down to the bottom and look at this news section. And the news section has the entries chronologically, right? So you can kind of go and see, okay, what's new since yesterday? So today, December 23rd, we can click on December 23rd and then see what's been posted all day today, all in one place without having to scan, right? So we'll also make, cover the other sites of information that USGS puts out, Facebook and Twitter, but this is kind of a good one to kind of look at first. So this was 8 a.m. this morning, and the lake surface had come up quite a bit. You can kind of see this is the northern vent and the western vent right here. Right, you can see this is the island right in here. And you can see these crust, these plates of lava crust separated by these hot shear zones, right? Places where the crust can actually slide past itself. And where the lava that's trapped underneath there is building heat and upwells and then breaks those crusts and splits them apart, right? There's all kinds of interesting processes that happen within lava lakes as they overturn their surfaces that we'll have to get into some other time. But kind of looking through the images here, this one is noteworthy just because you can really see how high up the lake level has come to this vent, right? You can kind of see on the side of the crater, we got this big sulfur patches. This is a big sulfur patch. Another big sulfur patch, right? These are things that, features we've seen for a while, but they're way up above the water lake. on the side of the steep hillside. And so it's amazing to see those now at what's become the new ground level. Yeah, right through there. And of course, you have to see that this is a massive source of all this gas coming out of here, right? We'll show you guys, like on a satellite image later on, how this is really a global phenomenon going across the whole Pacific. You can kind of see it all comes from these little holes, this one and the one right over here to the left as well. Right. At this point, this one looks more intermittent when this photograph was taken. It doesn't look quite as active. Still quite a lot of gas coming out of it, though. Right. So moving on, you guys can look at all these on your own. I'm just going to see what else I can annotate for you guys, and can really see, you know, how high that lava level is, right? That vent was bigger than this. Kind of was a line that extended down in this direction. So that lower part is below the level, right in there today already. You can kind of see that there's flow in this direction and in this direction, right? They're both splitting around this island that is still in the lake. And right, so this lava comes over this way, and this one comes around this way, and they meet, and they go, by this point they're cooling, right? So it can kind of go underneath into the third dimension underneath and kind of help the circulation of the pond in that direction. And so what this has been doing is, because the lava has been sinking down over here and over here, it's been pushing this island in this direction, right? And so you can kind of imagine, like, where the vent is putting the most lava into the pond, it's almost attracting, right? It's almost this drawing this island. And there's a second piece of island I'll point out on our thermal, which is over here, which is also drifting in that direction right over there. Right, so fantastic image. Of course, we see the scientist here who's taking measurements of the lava lake. So gas measurements, distance measurements, elevation measurements. Here's an interesting plot we'll come back to in a little while, but what they've actually done for us here is shown us on the left side estimated lava lake depth in meters, right? And the date going this direction. So you can see, we started off, first measurement, it was somewhere above 60 meters, then coming up to around 90 meters. And at 87 meters is this image over here on the right, right? So 87 meter image. And then the 156 meter image as it came up. Right over there. So you basically have what appears to be a curve. Let me see if I can draw a good curve with this mouse here, but something like that, right? Is the way this thing is climbing up. And that's expected because it's a pit. The pit is like a cone, right? It's got a pointy bottom. And as the lava rises up at the same filling rate, it becomes thinner, and every layer becomes slightly thinner, right? It spreads out across a larger and larger area as that thing gets higher and higher and higher. So you can expect the rate to not be a straight line going up, but rather for it to kind of bend over, curve over like that, right? That's the relationship that it actually has. So more on that in a little bit here. But here's another image of all this tephra, Pele's hairs, and other fine particles that are falling on the solar panels. This is a typical installation you might have, like in an instrument. I'm not sure what kind of collector this is over here, some kind of collector. You have your electronics and all your motherboards and things inside these kind of bins right in there, right? Power batteries, power sources. Your instrument might be in the ground. You see this kind of wires running everywhere. And once the data is collected, it goes into this radio antenna. And this radio antenna is the one that's beaming things back over to HVO. And that's how it makes it to the web or wherever else that we actually have a chance to consume it. We'll zoom out a little bit there. An example of those Pele's hairs, Pele's tears, kind of spatter bits, right? Those are all descriptive terms for different shapes of lava that come out of the vent. So lava comes out and it's kind of in a glob, and it's kind of splitting into lots of different fragments as it's falling down and out. If they fall down already solid, then they basically have cooled in midair and are often like a sphere or a tear shaped. If they fall still liquid, then they can actually splat and form what we call a spatter. Or if they're kind of a piece of a bubble that's expanding in the air and then that gets frozen in mid expanse explosion, right? Then you might get some fragments like these, like kind of thinner parts of it, right? And then it just looks like a tail of like a droplet of lava, and you can kind of see more droplets of lava there, and that's what the kind of example of tephra that's been coming out. So that's all the stuff that they've posted today. And I wanted to make sure that I covered a couple of things that I forgot yesterday. Yesterday I showed you guys this image of tephra, but it's also worth pointing out that they have this before and after picture of the thermal images. So in this early one, you can see before the lake filled all the way in, we already had an island, right? But the main fissure is up here. You can kind of see that it's really bright, kind of from here, like kind of in this area, up through there. It's not just at one elevation. It kind of has an upper elevation and a lower elevation, and then the lava lake level is now somewhere up in here, kind of burying it, right? But at this point in time, it's still kind of just all plunging straight down. The island is over here on the western side, and we have a lower fissure still exposed of the western side, right? By this point in time, that middle fissure and the lower one below it that was covered in lava are both stopped, right? And compare that to the 22nd, where you no longer see that buried fissure. The lava lake level is essentially coming up to the bottom of that eruptive vent, and by today, it's actually covered part of part of the bottom of that vent, as far as we can tell. So there's a video we showed you guys at the beginning. Let me zoom back out of here. And just show you guys, there's quite a lot of imagery in here that USGS is putting out. So moving right along, because there's a lot I want to show you guys. Let's kind of take a look at the most recent thermal images here. And what we have here is the most recent image. You can see that the lake, oh, I gotta change my pen color. In just a second. All right. So this is a northern vent. The western vent's kind of below the field of view right here. So we're kind of looking more or less from the northwest to the southeast, something like that, right? This is the island right in here, and here's that second little piece that I was telling you guys about. So let's look at the animation of this. So what we're looking at, the automatic animation put out by the USGS here, is a 24-hour time lapse. So for the last 24 hours, you can see quite clearly on this loop that the island starts off over here and ends up over here, right? And this little piece here as well is drifting. You kind of see what I was saying about how it seems to be being pulled towards this plunge pool, right, where the lava's dropping in from the vent. Right? And you can kind of see the circulation coming around the sides, both ways like that, right, and kind of curling in and pushing this way. Right? You can also see that this island's got some rough edges now. It doesn't have quite as many of those flat sides, right? This is what the USGS was talking about when they were saying that the edge of the island was being consumed. So let me pull up for you guys the entire sequence. So you can see from the very beginning how that island actually moved around. All right, and then let me open this for you guys. And so here's our sequence again. And I want to kind of pull it back here just so I can show you guys how this island actually evolves from the very beginning. So you can kind of see this is back on the 21st, so this is about 12 hours after eruption began. You can clearly see the islands over here. People have asked, why is there an island in there? Where did this thing actually come from? Is it related to the water that was in there? And I didn't have a chance to find the USGS update, but it seemed to me when I read it that it was almost implied that might have been a possibility, that first slug of lava that went into that big pond may have quenched and frozen or made some kind of slug that's forming the nugget, the core of that thing, right? So I'm not sure exactly. You know, it's a good idea. I'm not sure. You know, I just don't have enough information to judge on that. But that's something like that maybe would actually happen. What did actually birthed this island in the first place, right? So you can see in here that there's kind of a crack going right through there, and right through there. So this thing's going to actually split apart as we watch it. All right, you can kind of see now, at this point, we have one big piece, and then three separate little pieces over here. All right, and then more crust forming over there. Keep it going. I don't have the whole thing here in front of me. Let me try that again. All right. Sorry, you guys. This is one of those technical issue nights. This is probably part of going at this for so many days in a row. So here we go. Here is the one island, small island, and a big island right in here. You can see by the colors how hot this plunge pool is right in here, where the lava is plunging in from the northern vent right in there. And at this point, early on, we still see that lower western fissure vent still bubbling through the crust of the lake, right? This is an interesting case study because this is what we're talking about is what exactly happens when lava comes over top of the vent. Well, that happened already right down here. Let me rewind it for you guys. Right, that's kind of overexposed right there. But so in this image, you can kind of see here is our lower western fissure right in there. Right? Maybe I can get that bigger even for you guys. That's going to work. It's not going to work. But now you can see at some point the lava covers it over. You don't really see it quite as much. It's bubbling over here a little bit. And then you really don't see it much after that. So as the lake has continued to rise, right, we don't even see like any kind of, I mean, it's hard to tell from 1 hour by 1 hour frames. But it doesn't seem like there's any kind of upwelling over here. I mean, maybe it's still coming into it from below. That's a possibility. But for that to happen, you have to have enough pressure coming out of that one spot. And as we mentioned before, since this is a blade with different fingers, it could have essentially redirected whatever was going out of there to come out of here instead, or of this other one that's on a crater wall kind of below the field of view right in here. So that might be what happens with the other one over here as well. It might kind of bubble, and there's some several possibilities. It might actually feed it from below, in which case you would expect more circulation and kind of bubbling and sloshing, because all that gas that we saw that's coming out as a big plume now into the air straight from that vent where the lava is spattering would have to come up through that lake. And so that's going to cause a lake to start sloshing and bursting and you know, bubbles to be in it, and you know, more of the process of overturning. You know, it might be more of what we saw at Halemau'umau lava lake that existed up until 2018. So that's a possibility, right? And so that lava lake in 2018 is one worth talking about, because obviously it's a much different situation. The summit was much more inflated. It was a much higher elevation, so there was much more pressure in the whole system to sustain that. But that was a lava lake that was fed from below through a much bigger vent. We later found out, you know, it was kind of as it grew over time from below. But that's another possibility. So we've already mentioned when a vent gets drowned, one possibility of Kīlauea style, where it actually might turn it off entirely, allow it to repressurize, and then kind of go through in bursts. Once episode, another episode, another episode, another episode, with in-between times of draining back into the hole where it actually was coming from. Almost like just burping your baby, right? You know, there's all this gas coming out, and once the gas escapes, then the lava is flatter and then falls back down to the lowest possible place, and it goes into the pit, or in a case of the pit, having a lava level as full as the vent, back into the vent itself as well. Excuse me. So let's finish off the thermal images here. And so if I rewind this, right, here we go. Let's keep an eye on this block right here. And that block right there survives a rise in lava level. Its neighbor over here was completely consumed. That one disappears. You can see it's part of the big island attached by this big flat block. Right? It's kind of, there's this tall part which we now have learned is 150 meters across. It is also there's also a height I'll find for you guys in a little bit. And then we have kind of another little lump here with this kind of plane in between, right? So as we advance it, we see we've lost all that flat stuff, but we still have that one little spot right in there. That's the spot that when we look at our image now is the closest one to our vent. It's getting pulled in, right? And you can kind of see that our vent now, we only see a little bit sticking up above the lava level. Quite a lot of it is below that, right? In fact, if we go back to our actual live camera and reload it, we can get an even more current image. We can kind of see there's a brighter area right over here on the edge of the lake, right in there. And then a little bit of vent is still above the lake there. So we'll see, it seems like within the next day, we may see this encroaching further and further and further up, right? So I know you guys can't hear Dane. Dane is helping me out here on the tech side and online with you guys with the chat and the comments and all that stuff. So if you have any questions, you can feel free to shoot them to Dane. And I actually can hear Dane, so you can actually you can pass along questions to me or anything like that if you guys need. I will, for now, just skip to a couple of USGS questions that I picked out from their Facebook feed. And so here's one from Trevor Atkinson. It reads, "Is that a lava raft floating around? Awesome." And they reply, "Yes, in the center of the lava lake is an island that is about 30 to 50 feet above the surrounding lake surface." So there's a number I was looking for, you guys. "The island moves as if floating and is likely material erupted early in its eruption, accumulated at the base of Halemaku crater. We're watching it as well, and it looks like the island is shrinking as pieces calve off." So there you go. Someone else mentions if there's any sign of Anakin Skywalker down there. So there's a question coming in. If the eruption does not stop, can we have enough lava plan sustained? Is that essentially the gist of it? Yeah, so it's all about relieving the pressure that's built up inside of there, inside of the magma chamber in the ground. And that's something that we don't exactly know how it's going to play out. I did talk about this a little bit in some of my update yesterday, and I will bring that up again today. That there is a correlation between how much the lava is gushing, how fast it's coming out, and how long eruptions last. Usually, right? 2018 broke all the patterns because we had the summit collapse, and that kind of just screwed up the whole pattern. But since we don't have summit collapse anymore, since everything already collapsed and we're in a whole kind of blank slate, so to speak, in terms of that, we can look back at that historical record, right? And we can kind of compare, and we can see that most likely this eruption falls in the range of the other ones of a similar volume coming out of the ground, lasted from weeks to a month, which is kind of similar to what we saw after 1924's collapse, when there were 7 eruptions in the following 10 years. Longest one was about a month, and shortest one about 2 days, and most of them about 2 weeks, right? So that's kind of where we're coming from with that. So thanks for the question. We'll get to that a little bit more here in a little while as well. So next USGS question I've picked out, and if there's other ones coming in, just keep them coming. So this is coming right at addressing the issue we've been discussing straight up to the point. Do you anticipate a slowing of flow as back pressure pushes against the vent as a lava lake level increases? So they say, episodes of starting and stopping are common eruptions at Kīlauea. And yes, fountaining typically stops when vents are flooded to a point where the overpressure of the lava exceeds the pressure of magma rising from below. In those cases, lava from the lake pours back down into the vents. We've seen this before from Pu'o's early phases, as well as Kīlauea Iki in 1959. I showed you guys a video of that yesterday. And the video they're actually linked in their answer there. So same thing we're saying, which we're saying in different words, trying to explain it to you guys. This is we're all on the same page here today. So, okay, so Dan's gonna read me another question, and I'll repeat it and answer it for you guys. The vents spewing smoke, steam, and gas. The fumaroles. Which fumaroles? I'm not. So I mean, I mean, there's cracks across the entire summit. I'm not sure this is what you're getting at, but I'll try to answer it this way, right? There's cracks across the entire summit that allow all the gases and all the different magmatic systems underground, which can be, we're not sure exactly what shape they even are, how big any of them are, how they're all configured or stacked and all that, right? So there's kind of bits of them, all the different ideas. There's probably little bits of it everywhere. So the gas can kind of come out through those cracks, so it's kind of background level, right? It's probably worth saying that we haven't detected any increase in gases before the lava came out of the ground here, right? And part of that we suspected was because of the presence of groundwater, right? And so the difference from 2018 and the 10 years before that, when we had an open vent at Halema'uma'u, is all the gas could steam straight, could just vent straight out of there. And it acted as a central chimney, so to speak, right? And it was hot, and it kind of burned a ring around itself where water you can't have liquid water that close to where the lava is. So any water from the groundwater trying to come in close to that might have been vaporized to steam and caught up in that train and come out as part of the steaming column that adds to water that already comes from the magma, as well as carbon dioxide, as well as sulfur dioxide, as well as all kinds of other things that you guys can go read USGS if you want more information on that. Because we didn't have an open conduit with hot stuff that was preventing the gas from escaping, the water was able to come back in. So water was able to come back in because it was cold, and that might have been what prevented the gas from being detectable at the limits at the rates we've seen typically of other eruptions before. So what I'm trying to say is, we didn't see a gas signal perhaps because of the groundwater being so extensive across the whole summit that it was able to absorb most of the gas, right? It could also be that the actual confining pressure of the magma chamber that's left there underneath all that rubble isn't that great, right? Where it can't build up that much pressure and put out that much gas before it actually just physically pushes the rubble aside and is able to come out of the ground. So we'll await the answer from USGS on that, and maybe there's some more clarification on the question. Yeah. So right now the SO2 levels are a lot higher because there's an eruption. Yeah. Exactly. So once the lava comes out, it's coming out essentially because of the gas driving it upwards. Right. It's there's there's a certain nucleation depth, right, where the bubbles form, and for SO2 it's about a half mile down, and so below that level, all the gas is dissolved within the magma, right? You know, and I used an analogy yesterday of a bottle of champagne or soda or pop or whatever you want to, whatever your beverage of, you know, an analog of choice is. But in all those cases, you have a liquid inside the vessel under pressure with gas inside of it, right? Once you release the pressure by popping the top of the thing, then all the gas comes rushing out, especially in the case of champagne or if you shake the bottle of soda pop, right? And in that case, the gas is what's actually driving all that liquid to shoot out of there. And once the gas is out of the bottle, the bubble is burst, the gas escapes in you know, upwards, and the liquid falls back down as droplets. And that's essentially an eruption. But our liquid is lava and our gas is SO2. That's really the only difference. So when we have lava coming to the surface, especially when it's in some amount like we're seeing here, right, and it's able to nucleate SO2 and bring all of that all the way up, and all that gas is kind of forcing it to rise uncontrollably until it reaches the surface. Once it kind of starts that process, you kind of can't stop it anymore. Whereas below that half mile, you could actually park your lava, park your magma, right? It's still underground, it hasn't erupted, it's still magma. You can park your magma somewhere for a while, and it doesn't have to necessarily move upwards. Once it breaks that nucleation depth, then it's going to come all the way up. And once you crack your cork on your bottle of champagne, it's going to open, right? You can't kind of open your champagne cork. You either do or you don't, right? So it's kind of like that. And so once the cork is popped, then all the gas is going to come shooting out, and that's kind of what we saw. And so what you'd expect would be like a pulse with like a stronger, like more gas at the start, and then kind of leveling off. But we'll have to kind of wait and see what the measurements are from USGS once that's actually all compiled and released. So. Speaking of gas as well, you know, gas is really a big part of everything here, right? So this next question is here on the screen, you know, to the USGS from another viewer is, once the main fissure becomes drowned, do you believe spatter cones will develop? And so they say, there's been a lot of spattering and building of ramparts near the fissure vents, right? That's kind of fresher brown material we see around the orange on those videos. And that's just like the hardened lava is falling down, and when it falls and it makes those features, those are called ramparts. So spatter ramparts, as lava fountains and cascades down into the lake. Once the vent's drowned, we expect increased circulation beneath the surface and sloshing spattering against the crater walls. Already the lake's crust is very plate-like, reminding everyone of the previous lava lake that was active between 2008 and 2018. So there you go again. That's the gas factor. Okay, let me talk about Kīlauea first a little bit and kind of show this recap of Kīlauea when its event was submerged. Dane's relaying questions to me here, and he's relaying more questions about what happens when the event gets submerged. So this is a plot of Kīlauea's eruption in 1959. And on the left here, in this particular plot, is volume in millions of cubic yards. I'm going to change my color again so you guys can see easier. So volume, how much, and then time, how long over here, right? And what I've done is I've written in numbers over here with arrows to each point in time what the depth was of the lava lake within that crater. So what you guys can see here is that the lava filled the crater with a lot of volume because it was basically pouring down into the space below where the vent elevation was. The vent happened halfway up the crater wall. Once the lava reached the level of the vent, that's right here. on this plot, right? And so lava drains back for this period of the blue line. It's draining back down into the vent because the weight of the lava pushing down into the vent is greater than the built pressure of gas below there trying to get fresh lava out of there. So the gas is still there, but it's being counterbalanced, right? Now, of course, the gas is collecting, so you're going to get more and more and more and more gas at some point, because the gas is going to overpower the lava once again. And then it's going to come shooting up through the lake and put lava out again, start spattering again, right? And so what you see here is this little blip is such an event, right? This was phase 2, as I called it. And here you see phase 3. Right? But the actual amount of lava that was collected into the crater didn't change, because everything that got erupted above the vent level, once the gas escaped from it, the lava drained back into the hole. Right? And so it might be getting replaced with fresher magma that has more gas in it, but you kind of have this constant effect of you're losing gas volume, right? And you also have the denser lava going back down. So there's this whole dynamic in there. And then what happened, speaking of spatter and the lava falling around the vents and building features around itself, that happened in Kīlauea as well, and that happened halfway through the eruption, and that's this climb right over here. So because the spatter allowed the vent to essentially become taller, it grew out of the lake again. And once that happened, the lake was able to get deeper by that much, and it did that repeated drowning and restarting, drowning and restarting, another 12 times or so after that for the rest of the eruption. So this is just a good example to illustrate one possible pattern of what might happen, right? You know, is if you have not enough pressure, it could do that kind of back and forth and back and forth and back and forth. And at some point, there's just not enough pressure and the eruption would end. That's one possibility, right? The other one is, you know, that like the lake of Halima'o in 2018, you could have an open lava lake that just stays circulating and open, and the pressure coming from below is constant enough that you can't diminish it with the weight of the lake, right? Like if it's coming from a deep path, you know, from a shallow chamber and maybe from some deeper part of, I don't know, some pathway where it's not as easily obstructed, right? Where it has more momentum, or, you know, something along those lines. You know, maybe you have this open, sustained lava lake instead, right? But it's worth noting that the 2018 lava lake was at an average elevation of about 1,000 meters above sea level. The one we have now, if we're at 156, we're in a range of about 680 meters above sea level. So we're still 300 meters shy, 320 meters shy. It's almost 1,000 feet below where 2018 lava level actually was. And so you can imagine, you know, that extra amount of lava kind of coming up, right? And it's going to be harder to block, you know, something like that. So the fact that we're deep in the hole may make it, you know, I don't know. I mean, it may change the dynamics as far as how easy it is to sustain an open lava lake, right? If that makes sense. A little bit more about Kīlauea here. I'll go back into this paper, which is in 1981 by Waj, you know, Journal of Volcanology and just Research, talking about the magma discharge rates, right? And so this is, I'll zoom in here. Over here on the left, this is the discharge rate in cubic meters per second, right? And 50 and 100. So this first plot is a first 6 days, that first phase when everything was filling, right? And kind of see the eruption rate kind of started off climbing, then climbed faster, and at a certain point, it just started going down and it dropped off quite quickly, right? So that's kind of the pattern that it had normally when it didn't have any kind of backflow going on, right? And that kind of, in this upper plot over here, where they're looking at the cumulative volume, that kind of corresponds to this block on this side of the graph over here. And then we had the drain back happening in here, and then we had that renewed fountaining, and there is an extra volume that was produced from that, and again and again and again, right? So what you can see is that the eruption rate goes up, can go up, with the eruption lengths, the intervals of fountaining becoming shorter as time goes on, if you're able to drown events. You can have interesting dynamics like that as well, right? Where you're actually able to, as you're kind of building towards the end of eruption, like you're actually running out of built up gas pressure. It builds up, but then it kind of lets it off at a much higher rate, and then it's all the way down. Right, so that's interesting how that worked out in Kīlauea, and you can kind of see here this step plot is like how much backflow in total went back into the ground, right? So Kīlauea, it was very different in that sense, where there was other stuff going on like that, where a lot of lava was draining back into it as well. So that could be something else to watch if we get into a phase like that. As far as Kīlauea, that first phase is shown in this upper right panel right over here. And you can kind of see that put in 30 million cubic meters of lava into that crater, filling it up halfway, right? And of backflow, we had 1 million cubic meters in that sense. And during that episode, we actually had a net deflation, right? This is what I'm putting out here, is that allowed that magma chamber to depressurize, right? And if that would have been the end of that, then it could have ended like that. But what actually happened in 1959 is there was an extra injection of magma from below. And there's a whole lot more to talk about this. There's a very, very deep, unusual source of magma that kind of came to join the party, but without getting off on a tangent, suffice it to say that there was an extra 60 million cubic meters that came in from depth during the 2nd through 17th phases, right? So we had a whole lot of magma coming up, and that's why we had such huge, gigantic fountains during that eruption, the Hawaiian records. But most of that went back underground, 63 million cubic meters, 63 million, right? So by the estimate that we saw the USGS put out for yesterday was 12 million cubic meters. That's still a big number. But imagine, how much of that draining back into the earth, how that would screw up the whole equilibrium of what's underground, right? So that's something to watch for in the future as well. If you have very high eruption rates and lots of drain back happening at the same time, then it's kind of a perfect storm like that, right? So in the end, this eruption couldn't relieve all the pressure, and so there was a follow-up eruption that happened in Kapoho the following year. But Kīlauea was filled in the end with 38 million cubic meters of lava. So if our number is 12, or maybe we're up to some range of 15 or 13, 14 by now, we're more or less a third of what Kīlauea deposited during its historic 59 eruption. Now, because I did mention the Kapoho eruption, it's worth pointing out that Kīlauea was a very unique situation with a very deep magma coming from underground, right, adding to the eruption with this massive 63 million cubic meters of magma draining back underground, right? That's a denser, flat, degassed magma, right? Adding to the effect, and the fact that unlike then, we now have a post-caldera collapse situation, whereas in 59 we didn't, right? There was an eruption earlier in 55, and a small pit had formed in the summit of Kīlauea, but there was nothing nearly the size of what we have now. So there are all those other factors that kind of build towards a situation where it was able to open a path all the way down to the East Rift Zone, to the lower East Rift Zone, right? And that's what rift zones do. We always hope that happens later than sooner, but with rift zones, geologically, it's a certainty that they're going to erupt again. So there's always a geologic risk that's involved with rift zones, and that's just something that everyone has to come to their own terms with, right? Balancing out the benefits of living in areas that are very tropical and lush and have very vibrant communities and like-minded people and that kind of thing, against geologic risks and lava hazards and things like that, right? So we don't see any signals today of the activity at the summit of the volcano moving anywhere past into the East Rift Zone. So there's no change in any of the risk to the lower East Rift Zone, just kind of make that clear, right? But the pathway is a pathway. It's always going to be a pathway, and it's always going to be some risk, and that's my job as a geologist to kind of inform you guys of that part of it. right? So without belaboring that point too much, we can talk about that more in the future. We can finish off Kīlauea here, right? So are there more questions about the filling, Dane, that you can relay to me? All right, so if there's more questions about the filling, then we can address them later on in our broadcast, yeah? So you can type them in or whatever. All right, so what I want to look at now is this contour map that we produced based on a USGS data release, digital elevation map. And so we produced this to show you guys the shape of that inner pit. And I realize you guys probably can't read a lot of this. I'm just gonna zoom in way more, right? But the bottom of the pit down here is at 520 meters, right? That's the lowest part of this pit. You can kind of see that all these close together lines all through here, all the way up. This is that really steep wall. And so this flat spot right here is a first ledge you kind of see, right? You kind of see the edge of that big cliff is kind of right through here, there, something like that, right? And it kind of gets quite a bit taller on this side, right? So that part of the pit is very steep. There's one exception being this one lowest block down here. That was the one piece of that old crater floor, and now we know that's been completely covered and buried, so that's not even a factor anymore, right? So question kind of following up, like if we did have a sustained lava lake for a long time here, and it were to fill up all this pit all the way up, where would it actually spill over? So that's what we can use this contour map for. We can kind of see that right now, there's the lava lake is on the order of 160 meters, 150 meters, like that, above the bottom of this pit. So from 520, that puts us up to 660 to 670 to 680 or so. So that's in the range of somewhere right in here, right? Something like that. And forgive my mouse work here, but that's more or less the shape of the lava lake we have now, right? So for it to get to the top up here, it has to come up another 100, let's see, from 660 to 800, another 140 meters. That's about, what, maybe 500 feet? 400 feet, somewhere near. So that's still quite a ways to go, right? It's got to come like the same vertical distance upwards that it did already, and it has to do that while the crater is getting wider and wider and wider the higher up you go, right? So how can we actually like reconcile this and figure out what's really going on here? Well, one thing is to take this USGS data of the lava lake depth, right? And they're giving us discrete points in time where they're telling us how deep the lava is at certain points in time. And they're also giving us, from an earlier update, a volume with that corresponding to that depth. And so what we can do is, let me show you guys this part over here first. We can kind of draw a conceptual model and kind of approximate by using a cone, right? This is essentially the shape of our crater. Not exactly. We have an oval instead of a circle up here, but for the rough calculations we're going to do here, that's going to be good enough, right? So if you know both the depth of the lake and its volume, right, then you can figure out its average radius here, and from so you can kind of from there you can kind of get some other calculations, right? So using that kind of approach, we've plotted on here what we expect the current rate of increase of the flow to be. So if I zoom in here a little bit more, this first part here where we have these 4 green dots, these are the real USGS measurements right here. This is a real data right here. So 134 meters, 143 meters, 156 meters. And so we've taken that kind of pattern and we've fit that kind of trend, right, to see that same pattern of increase and then how long would it take to get to the 800 meter level, right? So, but down here, this part of it is actually just the actual depth of the lake. And since we're starting at 520 elevation, the bottom of that pit, then elevation we're looking for is actually up here, right? So you can see that down here we have dates in the bottom. This is 2 days for every square that you guys are seeing here. Yeah. So today we're still right here. This is how far we are, right? So this projection is going way off into the future here. We're only on day 3 of this eruption. And here you can see day 0, day 1, day 2, day 3. To reach the 800 meter depth over here, it would take us until day 14 or 15, right? That would be January 4th after the new year, right? Now there's a big if here. The big if being that the rate of filling, the rate that the lava is coming out of that hole doesn't change. Now, we've just talked about all these different ways that the thing could actually change. It could start, stop, start, stop. It could be having to put the gas out through the lake. There could be all kinds of things could happen, right? So this is a very rough back of the envelope kind of calculation. It doesn't look like the back of an envelope right here, but that's essentially what it is. And you can kind of see that it would take about 2 weeks, right? And we're 3 days into it, and would have to sustain what it's been doing for the past 3 days, which has been amazing for all of us to see how quickly that lava has filled up all the way to reach the level of that vent, just in 3 to 4 days. Yeah. It has to keep up that same rate as it drowns a vent and comes up again. And if that happens, then in another 10 days or so from now, it may spill over onto that flat area. And that's what that would look like, right? So we've kind of drawn here the 800 meter contour, and everything inside it in red, and that would be the shape, and the spillover would be happening on this ledge over here, and then probably a little bit over here as well. Now, those are the first places where it's going to start spilling over. Well, but then what? Well, then it's inside of another crater, and the crater is about this size, like this. Okay. Then it's going to fill that one up. Then it's a whole new game from there, right? And so our cone doesn't fit that shape anymore. It doesn't really apply, and kind of it's a whole new game, right? So that's kind of the initial answer right there. It has to fill that up to kind of overflow into here, and if it does that, it can kind of spill into these areas, and eventually it can kind of get to a point where it can fill in more of a broad area like this, right? Kind of also spilling onto here eventually as well. But that's not guaranteed to happen this eruption. You'd have to sustain this rate, as we said, for another 10 days without any change, right? But as eruptions start and stop, there could be some future eruption that fills this pit to this point and spills over. And so that's interesting to see how this changes, right? Assuming the earthquakes or ground sagging and all those kind of more minor changes don't affect the overall structure of the contours as we're portraying it here. Yeah. So there's another view of that, kind of with the satellite image background here. So you guys can kind of see what that would look like, maybe more visually, right? Maybe someday we'll have a picture and it looks more like this, but this will all be black or red and steaming or something like that. Yeah. Right. It's worth pointing out that right now there's 2 overlooks that are kind of the closest ones. This one is the Kīlauea Kīlauea overlook, as it's called. The old Jagger Museum sits over here, but it's close to the public. So anyone visiting a park can't go past there. They have to kind of come over here. And you can walk a little bit back and forth along. There's kind of good view spots of the glowing area all along the crater rim, all around, right? But there's also a trail that goes to Kīlauea over this way. And it's close to cars. You have to walk the road over here. But you can actually stand and overlook over here and also try to look off in this direction. So those are kind of two closest places we actually could be. And so another question we've been getting is, and it's related to what we've been talking about, the lava level rising and how fast would it rise, and when could I see it, right? So what I've plotted here is a profile from Kīlauea being over here, and this is basically south, north, over here. What's obstructing the view of the innermost pit over here is the ledge of that other crater, right? So what you really need to do is be able to see past that edge. And so you need the lava to rise to this level for you to see past that way, right? And so by our rough calculations, the lava level would have to be at 757 meters elevation. And when it got to that point, you would be 2 kilometers away from it sideways, right? So over a mile away. From the northern viewpoint, it's a little bit different because the terrain is slightly different on that side, right? So you have to look a little bit higher ground right over here. And so that puts the line of sight at 779 meters, right? A similar distance, about 2,000 meters away, 2 kilometers away. So 757, 779, and let me go back to this one. 757 could be day 8 or 9. 779 could be day 11 or 12, right? So we're talking about if it were to sustain that rate without any change, which seems unlikely, honestly, but if it were, then you'd have to wait another 5 days-ish to be able to see it from the south, and maybe another 7 days-ish to see it from the north. Just the very edge of it, right? And of course, the higher and higher it comes, the glow is going to get brighter and brighter and brighter and brighter every night, right? Even if it comes up, more slowly than that, that'll be the case. All right, so that's kind of that answer to that question that kind of had us going for a while there. And I want to bring up, this is another plot from that magma discharge rate, which I think refers to as well something we were talking about earlier. So for those of you guys that didn't see the update yesterday, this is a plot showing on one axis over here, meters per second, the eruption rate of the volcano, right? So we have, it's a log scale, 1, 10, 100, 1,000, right? On this other axis over here is duration of the eruption in days. So 0.1 days, 1 day, 10 days, 100 days, 1,000 days, right? And what they see is a trend like this, such that if you have very high eruption rates, you tend to have very short duration in days, right? Now, this is kind of a historical pattern up to 1981. So what happened since 1981? Well, pool eruption lasted 35 years, right? So I'm not sure how many days that is, but it's way over here on this end of the graph. And its average output rate is somewhere around 4 cubic meters per second. So 4 plots around, so that Pu'u'o will probably plot somewhere right around here. That's Pu'u'o. Not that far off the trend, right? Well, what about 2018 in Leilani? Well, if you remember, we were looking at science paper, right? And looking at some of these measurements of bokeh fusion rates that now it's I have to stop here and just kind of, say something I didn't have a chance to see yesterday, which is that it's tricky to measure these things because every lava flow has a different amount of gas in it. So the amount of stuff that comes out is determined by how much gas is in it and by how much the gas is swollen. So the real best way to compare these things is to kind of measure it with the gas, then get a sample of it, figure out how much of it's gas, and then subtract the gas out of it, and then figure out how much is what they call the dense rock equivalent of that. So you can actually have an eruption rate that, that's essentially takes out the gas. And when we're looking at eruption now in 2020, we're looking at these rates, bulk rates in 2018. We're looking at that with the gas in it. Yeah. So with that caveat, we are in a range of 2,000, between 500 and 2,000 cubic meters per second, right? What's coming out of Fissure 8. And this is relating to the long-term surges being pressure driven, right? And we also noted that there were shorter term variations, pulsations that got as high as 3,500 cubic meters per second. Caveat with the gas, right? And so if this is a super, super gas rich phase, then this is kind of, artificially high because there's a lot of gas in it, right? So really we see one cluster that's here and one cluster that's here. So you really can believe, it's certainly between 2,000 and 2,500 and certainly between 500 and 1,000, right? That's kind of where it is, right? So now this science paper that was put out by USGS scientists does address this very issue. And I know you guys probably can't read this, but I'll draw it on here in case anyone does say, right? But they say peak level surges of 1,400 to 1,700 cubic meters per second relate to 400 to 500 cubic meters per second for dense rock equivalent effusion rate, right? So taking out that caveat, we're at a 400 to 500 perhaps value there to kind of compare what we're seeing in some of these other places, right? So even still, if we're at 500 or 1,000 in that range, that would put us kind of in the range up in here. And our duration was about 100 days, so our point is somewhere up in here for 2018. Right? So that one was kind of off the pattern, but the overall trend kind of holds like that, right? So, and that's why when we see what we've calculated as eruption rates now, and USGS has kind of said, given a range of somewhere between 60 to 90, they've said 100, they've said 60, that's more or less the range. I think for the entire eruption, if you calculate from 12 million going back, the number I got was 71. So 71 puts us on this line right over here. You can kind of see that there's eruptions that last from there all the way to, well, maybe there, if we count this one down in here, right? So that's between 1 day and in this case, like 50 days or something like that, if we go to the outer end. If we take this point over here, that puts it at 20 days, right? And so this is part of the rationale until we see something to cause us to believe differently. Why would expect this eruption to not be a long-lasting eruption at the summit? But of course, there's all of that dynamics we talked about already that are other complicating factors as well. All right, did I get it, Dane? All right. So I'll take another question. I'll listen to Dane here for a second. Okay, so the question is, how hot would the lava lake stay today if it were to stop erupting and become all the way solid, right? Which is a good question. So that depends a lot on the depth, and that brings up the Kīlauea analog as well, because during a Kīlauea eruption, that was measured. Kīlauea is the only example we have of where scientists have actually drilled through the cooling crust into the core of the lava lake repeatedly for years after it stopped erupting. And so we have a whole profile. I have a plot that I can bring up for maybe our next update that shows that. But essentially, in the case of Kīlauea, it's still hot today, and it's been 61 years. Is that right? 61 years. Still hot, still steams. When it rains, the crater floor still steams, which means the core of that solid rock is still above the boiling point of water, right? And Kīlauea ended up being 440 feet thick. Ended up being the total thickness of that lake. It was quite a bit wider than the pit of Halemaumau, right, that we have now, right? So that's a big difference. It was quite a lot wider, but as far as thickness, the thickness could have a similar kind of thing. 440 feet thick. It's still hot 61 years later. So that's ballpark for how long this that could actually stay hot. Yeah. All right, so we've kind of gone through a lot of the nuance of how the lava was rising and the contours, all of that. I'm going to get back to some of the USGS products they're putting out here. So one thing I wanted to point out is that USGS has a maps page, but we haven't pointed out to you guys yet, right? But if you look on a sidebar or in a top menu, you actually can get the maps page. You can find all kinds of other things here that are not coming out in other media, right? So, for example, today was issued a preliminary summit depth lake. So here they've labeled north and west vents, and they've drawn estimated lava depth in feet meters, and they kind of have it based on a DEM right over there, right? And so we won't belabor that, but you can kind of see they have one for overlaying a thermal image, right? They've actually flown over, taken thermal cameras, and then superimpose that thermal imagery on the landscape, right? So you can kind of see where the new lava, you can see the island here in the middle, you can clearly see the vents, right? Side. Right, so they put out more depth rates. The reference map is in there. The INSAR, right, is something that goes back. There's been quite a lot put out over the last few days here. So moving on, these things quite often come into Facebook as well. And so if you're not checking the other places and you're only on Facebook, it is worth looking at USGS volcanoes on Facebook. You can kind of see that all the videos and pictures we're showing you guys are all in here. Although I forgot to load this one up right here. So maybe just zoom in on it, you guys here. This is actually a radar imagery that has been just released. And so it's just like a scan out of a satellite. And it's showing the change from a water lake to a lava lake and showing the vents here as well. So for example, there's that one. Image of the scientists measuring the gas. Picture by Janice Way, park photographer, of the moonbow on the first night over the volcano. That's something worth everyone seeing right there. Yeah, someone has called her Janice Way Cool. Yeah, if you guys want to call her that, and hit her up on Hawaii Volcanoes National Park Facebook. Yep, you can find her there. So once again, you guys can go through and look at all of this. It's kind of all the same things we've been showing you guys. So let's move on to some of the monitoring signals here. We have here the Hawaii short-term SO2 advisory page. And you can see that on a short term, I'll reload it. On the short term, we have Hilo coming in at 0.013 SO2, Kona 0.003, Mountain View 0.04, Ocean View 0.03, the highest one there so far, and Lehu 0.003. Right, so on this map, they all show as green. Where you look, right? This is just SO2, right? Now, one thing that happens after the gas comes out of the volcano is it interacts with all the moisture in the air and with the sunlight, and it creates particulates that are sulfates, and those can travel downwind and also affect air quality, right? In other ways and beyond just SO2. And so I like to look at this overall Department of Health, State of Hawaii air quality map, which has all these different factors on it here. So we could look at just SO2, for example, and see that, yes, everything is green, with just SO2 on all the islands. Right. Right, okay, I think oh, here we go. So let me just finish off talking about, if I can get my browser to respond here. It's not doing too well. But if you were to click on all, you can actually go to the particulates. You actually can see that Ocean View is not doing quite as well. So I think I'm just gonna not fight it right there and instead go to the park gas thing. We'll finish off the gas here, then we'll talk about a question that came in from Dane about magma ascent rates here. But so you guys can see that in the past, we've mostly had the gas at this lowest station, Kahuku, which is kind of in the South Hawaii, right? And so they had some bad gas earlier today and some bad particulate matter over here. But if you look on this graph, we also have other parts of the park today having, in the orange and in the reds. Like here's a Namakani Payo campground at the summit of Kīlauea, right? And Kīlauea Visitor Center, look, they're off the charts in particulate matter level here. So this is actually an effect of the wind. We'll show you guys that actually. I'm gonna skip ahead. Let me skip ahead to this tweet by Simon Karn, who is releasing the GOES satellite, right? Who's actually showing us Kīlauea plume right in here. It's showing us drifting to the north during this sequence, right? Whereas typically we've seen it drifting off in that direction to the southwest. So if this thing starts drifting to the north, then it makes sense that you would see more measurements in Hilo as well as in Volcano, where the park sits, right? So the VOG map project also has updated their models, so you can kind of see this was their model for today, and then kind of see it did not take into account that change in the winds, at least not so far in animation. You can see it's slacking a little bit, getting a little bit of flow there, but not that much. Right, so maybe tomorrow we'll see a different pattern of this. And kind of zooming out and looking at the statewide level here, you can kind of see there also the trio is shooting way off into the Pacific here. So let me try to reload this one here and see what I get. All right. So air quality index for the whole state, you can kind of see that everything is green, even on other islands, except for really ocean view over here in the middle of Hawaii Island, right in here. And so we can actually click on these and see some history, although it does kind of see it's been high all day. Ocean view yesterday. And finally, last thing in the gas here, the windy model showing this massive cloud of SO2 sitting in mid-Pacific here, surrounding Hawaii, right? Okay, so we had a question about the ascent rates and the difference between eruption rate and magma ascent rate, perhaps, because we're talking about how fast is the magma coming out of the ground here, right? And not how fast it's filling into the magma chamber below. So right now, if you'll recall, I have it up here. Let me come over here. If you guys will recall the INSAR that was released by the USGS, which is a plot of the deformation in the volcano showing the change in the ground level between two successive passes of a satellite that's scanning it with a radar, right? They're showing the ground sinking in a wide area right over here, while the ground is rising in an area very near the eruption site right over here. So because this is massively important, because there's several things that I've said today already, because the ground is actually sinking over here, what this is telling us is that the rate of magma coming into this pocket that's feeding this area is less than the rate that is coming out of the ground, or else this thing wouldn't be deflating, it wouldn't be sagging like this, right? We'd have a Kīlauea situation where the thing was actually still swelling even as it's erupting, right? And if that were the case, we were in for more developments in the future, right? Whereas now we're seeing the opposite. We're seeing it sagging, right? So whatever amount is coming in is less than it's coming out during this eruption, right? And that makes sense because it hasn't been coming out for 2 years. It's trying to catch up, right? All that back pressure is built up. So for what comes into that lower area, so maybe it's worth kind of pointing out once again, like the eruption area. We also have this area over here, which is the area of intrusion that happened December 2nd. And we talked about how if we look at what the USGS has proposed as far as the magma storage zone being beneath the eastern part of that pit, that rectangle they drew is essentially like in there, right? The eruption site is like over here. So you can imagine that a magma body could put up injections in both of those directions. Like in map view, it would look like the magma source here, feeding an eruption and feeding an intrusion both, right? So that's basically the difference there, is that they're independent of each other, and what comes out of the ground is a result of what's been built up over time. Whereas we generally consider what's coming in from below to be more of a long-term average supply rate, like there's kind of a constant, steady supply of it, right? It doesn't, even though there are many areas in between where it can stop and store and stop and store and stop and store, it kind of can trickle and a little bit, kind of knock, create an effect where magma is a net effect rising. All right, so that's the difference between the ascent rate and the eruption rate. So we just check Simon and Karen on Twitter, and just gonna kind of show you guys, like, we find tweets like that by looking at USGS Volcano's Twitter as well, and so kind of another good place to look, not only for the imagery that they collect, but also when they interact with other researchers, like Dr. Karen at Michigan Tech. Yeah. As if they're retweeted right over here, right? So moving on from that as well. So I wanted to point out once again that we do have still continuing FAA flight restriction. It is still at 3 miles, 9,000 feet above sea level, right? We'll move on. Our deformation signals over here. As far as our tilt, we have to kind of back up to look at the whole past month view once again. You can see that by now, we've dropped down from 10 to minus 25, so about minus 35 microradians so far, right? And that kind of compares to the injection we had earlier that was independent but offset the ground by maybe, let's see, from minus 10 to in the range of 15 or so, right? So that's a long-term pattern. You don't see much on that particular tilt meter. But it is worth pointing out that some of the other tilt meters, like if we look at the escape road tilt meter here, right? This is down the rift zone a little bit. You can kind of see that just on the 21st, right, there was an event, perhaps an earthquake, that happened, right? After that earthquake moved, I'm not sure if this is that south flank earthquake or if it's a different earthquake. But after that earthquake, essentially changed the dynamics there. We see an adjustment by the north component primarily, although a little bit also in the east component of this station. Now, it's not exactly clear. We have to look at a map and go into more detail than I want to spend time on this today. But you can imagine that as pressure is relieved from the main summit area up in here, that areas like Escape Road, which is on this map, that station is somewhere right in here, right? The East Rift Zone runs like this, and it kind of bends over in this direction, right? So if your station is right here, and its thing is tipping, its north component's moving, then there's some change in the rift zone that's right next to it. So it's not clear if the magma that's in the rift zone here is moving back towards the crater, or if there's some, what exactly is happening back and forth here. We're gonna have to look into this in more detail and keep an eye on it here in the future for you guys. But it's worth pointing out that signal does exist there. Right, okay, so now we're on an earthquakes page. You guys can see that, once again, very few earthquakes. I'll zoom out here to the island map, but you can see only a few, that one and that one, south flank earthquakes, this one right on the East Rift, and only a few summit earthquakes as well, right? We do have one that just came up up here in a flank of Mauna Loa as well. So those are earthquakes, they're still low, and that covers all the data I want to bring to you guys today. I know we've been going on for a while, and I do appreciate you guys sticking with us. I did intend to cover more of the history of the caldera, collapsing and refilling today. I intended to cover the geologic map and overflows of the lava lake as well, but with all our tech difficulties that had us getting a late start and everything that's going on today, and I think we're gonna have to leave that until tomorrow once again. So thanks for sticking with us. Apologies to you guys for apologies to Dane, who no one can hear. Yeah, but that's kind of the bulk of information. So we are part of the Hawaii Tracker team, and we are brought to you guys by Hawaii Tracker. This is hawaiitracker.com page, right? That we make sure we compile all our information as well. Here, it might be a little easier to find things here than on Facebook sometimes, right? So you guys can check this out, and this is a good way where if any of you guys would like to support the work we do, there's a donate button over here as well. So we would appreciate you guys helping us overcome our challenges that we're facing here. Yeah, and along those lines, we'd like to thank. We've had several donations already today, and I'd like to thank Eileen P, Becky B, Sherry Van R, Joanne O, Dorothy T, Harry S, Martha D, Denise J for becoming month supporters. Nancy M, Jessica F, Katarina P, Helen R, Aaron B. Thank you guys so much for your donations. It means a lot to us. It helps us a lot keep our work going. Especially when it's pedal to metal, like when Eruption busts open and things change quickly, like they're happening now. So we appreciate your support. Please visit hawaiitracker.com. You can check us out on Facebook as well. We have all of our Facebook streams, all kinds of other activity as well. And we also are on YouTube as well under the Hawaii Pod channel for you guys who are catching us one way or the other. So unless there are any other questions that I need to address, I think I will wrap it up there. And on behalf of Dan and myself, say mahalo to you guys. Thanks for joining us for another update. We'll work out some of these kinks tomorrow, bring you guys some audio from Dane, and get to those other topics I wanted to address for you guys as well, including the history of crater collapses. Very briefly, the caldera has collapsed and refilled many times in the past. We often can't see exactly how quickly that happened, but we can talk about that tomorrow. There have been times when lava lake has kind of come up and spilled over onto the crater floor before, and we can look at the patterns of that and see when that happened and what's left over and what where those pieces of lava actually are now. So those are kind of a couple of topics we want to address tomorrow, as well as kind of revisiting some of the other episodes like the summit in 1952 and 1967, which have been analogs pointed out by USGS as possible having similarities in certain ways with what's happening now in 2020. So thank you guys. Thanks you guys for joining in. Mahalo from Dana and myself. Aloha.